Archimedes lived more than 2,000 years ago. He was born in 287 BC and died in 212 BC. And during his lifetime, he undertook an amazing number of different projects and did studies in science and mathematics and engineering. And I'm going to just describe one of these today. This is what's called Archimedes' principle, or the theory of buoyancy. And it's what we would now call part of the field of hydrostatics. There was a reason that he developed this theory, and that was because Hiero II was the king of Syracuse at the time when Archimedes was alive. And the king had given recently the goldsmith a certain amount of gold and asked him to make him a new crown with that gold. When the gold crown was delivered to the king, he had some suspicion that the goldsmith was trying to cheat him. And so he asked Archimedes whether there was some way that he could figure out to determine whether that crown was really pure gold or not. And of course, without in any way damaging the crown or altering anything on it. So this is the method that Archimedes thought of to answer that question, and it's called the theory of buoyancy now. I'm going to start by taking a box and immersing it into a swimming pool, and that's illustrated on this first figure on the left-hand side of the figure. The box is going to have a 1 square inch top and 1 square inch bottom, so 1 inch by 1 inch on the top and on the bottom, and it's 1 foot high. Now, as you know, if you dive into a swimming pool or a lake or the ocean and you go deeper and deeper, the pressure keeps on getting higher and higher. And that's naturally because there's more water above you pushing down. So in the middle of this panel, I've put in some numbers for this. The weight of the water in that particular box I selected, if you filled it with water and weighed it, it's 0.432 pounds. That's how much that much water weighs. And so since the top of the box is 4 feet deep in the water, at a depth of 4 feet, the water pressure would be 4 times that 0.432 pounds on every square inch, and so that the pressure would be 1.73 pounds per square inch at a depth of 4 feet, and that would be pressing downward on the top of the box. Now the bottom of the box is at 5 feet depth, and so at that depth, the force on the bottom of the box would be 2.16 pounds. And of course, the difference between those two, that's what's called buoyancy force. The difference between how much the water is pressing down on the top and up on the bottom of the box, that's the buoyancy on the box. And that has to exactly equal the weight of the water that was displaced by the box. Because if that box was filled with water, then you could think of it as an imaginary box just floating there. The water is stationary, and therefore the upward buoyancy force on that amount of water has to exactly equal the weight of the water, so that the water would be stationary and floating at a certain depth. And that works for any shape amount of water or box. And on the right-hand side of this slide, I've shaded in a little bit of water and put an imaginary box around it of a funny shape. So that's water that's really just in the swimming pool. There's no real box, but that's just an imaginary box that's drawn around that some arbitrary march of water. And so that water inside that arbitrary box weighs something, and it's sitting there. And so you could say that the net force from all the surface, all the water, or all around the surface, all those curved surfaces of it, the net upward force has to exactly equal point, or whatever the weight of the water is there, because the water is stationary. So that the upward buoyancy force on that water is exactly equal to the weight of the water that's been displaced. So that's a theorem that Archimedes discovered, and he wants to use this now to find out whether the crown was pure gold or not. So the way he did that would probably be the one that's shown in the second figure, and that uses a thing like a seesaw, or chemical balance it's called nowadays. There's a fulcrum in the center, and then that horizontal line is a bar across the top of that fulcrum, and you put equal amounts of you hang two things on the two ends of the seesaw or the fulcrum, and one end being the crown and the other being some weights to balance it. And so when you make that horizontal bar horizontal, then you've got the same weight on the left side of the fulcrum as you do the crown is on the right side. When the crown is underwater, it's displacing some of that water, so there is a buoyancy force on the crown that's pushing upward somewhat. And so he would put on some weight, whatever weight's needed on the left-hand side, so that that balance that line is horizontal. Then he would do the same thing with the crown when it's out of the water. And so when it's out of the water, there's no buoyancy force from the water because there's no water displaced. And so he's measuring the actual weight of the crown in air. And he would have had to add a little delta W, some amount of extra weight, in order to balance the crown when it's out of air compared to the amount of weight that was there previously when he was balancing it underwater. And that delta W is a thing that Archimedes had to measure. So we'll see now what he did with that by putting in some numbers, and that's going to be done on this third figure. So first thing he has to do is to determine what's called the specific gravity of gold. And this is done by taking, say, an ingot of 1 cubic inch ingot of gold, or it could be any size, but I'll just use 1 cubic inch as an example. 1 cubic inch of gold, and weighing that, and then weighing 1 cubic inch of water, and taking the ratio of those two numbers, and it turns out that for gold, that's 19.3. So gold is roughly, any amount of gold, any volume of gold, weighs about 19 times as much as the equal volume of water. So when you put the gold into the water and weigh it, it will weigh 1/19 less than the weight it would have been in air. If you did the same thing for silver, the specific gravity of silver would come out to be 10.6. So silver is a lot denser than water, but less dense than gold. Now, the number 3 pounds, the weight of the crown in air, is just a number I made up. It's not really the actual crown, but it's just an example of what the calculations that Archimedes would have gone through. So there's some weight of gold that the king gave to the goldsmith, and I'm assuming it's 3 pounds. So if it had been pure gold, the delta W, in other words, the difference between the weight of the crown when it's submerged and when it's in air, would have been 1/19 less than the amount of weight that the crown weighed when it was in air. And so that's the buoyancy force, is 1/19 of the weight of the crown, because it would have displaced 1/19 of its weight in water. And that turns out to be 2.5 ounces. So we take the 3 pounds and divide by that 19.3 and get 2.5 ounces. If it had been a pure silver crown, then you'd take the 3 pounds of the crown weight and divided it by that specific gravity of silver, and you would have got 4.5 ounces. So what Archimedes really had to do was to see whether if it had been a 3-pound crown, whether the weight, this delta W weight, was more or not more than 2.5 ounces. And so if it was significantly more than that, then you could say that the crown was not pure gold. For example, if the goldsmith had taken the 3 pounds of gold, kept 1.5 pounds for himself, and substituted for that 1.5 pounds of silver and melted that together and made the crown out of that, then this delta W would have turned out to be somewhere around 3.5 ounces. And what Archimedes actually found was that was not pure gold, and that the weight was significantly more than 2.5 ounces or whatever he would have gotten given his actual amount of gold that was given to the goldsmith. Anyway, that was the way that this Archimedes principle, or the buoyancy effect, was first discovered, and is just a story that's been passed down for many years.